Welcome back. We're going to be examining a little bit more about analysis of variance. We're going to be exploring the factorial analysis of variance, and in this case we're going to really look at fixed effects models. This is just to give you a quick outline, help you out with some of the reading in our textbook that we use in this class. So one-way analysis of variance, sort of as a review, what happens when we have more than one factor. So in some of our other videos we talk about one-way ANOVA, and we talk about it with one factor for one way and one independent variable. So we could care about achievement in statistics class. We want to know if practice and online videos would improve achievement. So those are some factors we could be exploring. In class we played around with M&Ms. We played around with difference between M&M size. Between M&M type, whether they were peanut M&Ms or plain M&Ms. But now imagine if we were to go explore like two different factories, and I have another video about main effects and interactions for you guys to watch that I'll focus on that, so I won't talk too much about that in this video. So let's design the experiment. What could we do? Well, we could do two one-way ANOVAs. We could test each factor separately, which is fine. But we'll lose a little something. In a factorial model, when we design this, what we actually gain is we gain the ability to examine an interaction effect. Again, I'll point you back toward that video where I explored the interaction effects in Excel, because I think that visually will describe to you what the interactions might look like. So we could have a single design, we have one big analysis, and we can look at both main effects and interaction effects. So this extends the ANOVA framework. We basically still keep the same assumptions. We can still interpret main effects and interaction effects. Main effects, but now we can add in interaction effects as well. So the frame of the factorial model will help us understand what the two-factor model looks like. So the characteristics here, this is also, please read your text if you're looking at this from my class, the Lomax and Housefall second course text. We extend one-way ANOVA. In this case, we have two more independent variables. Most of the time in class, examples are going to be two. Maybe we'll do a three independent variable, but you can have as many as you find reasonable. You're going to have trouble if you start putting in 4 and 5 interactions, way interactions, trying to explain what those are. But when you have two or more independent variables, we have a factorial design. We can test the main effects and interactions. Multiple main effects can be studied in one model, which is very advantageous. Interaction effects can help us determine if factors are operating independently or whether they're moving together somehow. And we can look at the additional impact, which is the interaction effect, which you wouldn't be able to test if you did two one-way ANOVAs. If the model is designed separately, we would not learn of this influence of the interaction effect. So the main effect of a factor averaged across the levels of other factors of the dependent variable. So with two factors, effects of factor A are averaged across level B, and conversely, the effects of level B are factored across level A. And you'll also see that I go over that example with our other video for main effects and interactions. Interactions I like to think of as the cell level difference. So we combine more than one factor. We combine them. Factors are considered separately, but we can look at each cell individually, and the mean of the patterns can be plotted and tested. And those graphs interactions, again, are in my other video, just specifically targeted toward main effects and interactions. So what's the advantage of having fixed effects model? Well, we can reduce the error variance. Unexplained variation by the first factor may be explained by the second factor. We have more precise and powerful model. That's useful for us. In most cases, it's possible, very, very, rare not rare, but very specific circumstances where there's no interaction effect. You basically, and no other main effect. You could be removing power just by a degree of freedom issue. Improves economy of resources by far because you're putting everything into one model instead of having to test them separately. Generalizes to more situations. So now in our class, if we wanted to know are all M&M factories equal, across different types of bags. So we have plain M&Ms and peanut M&Ms, and we want to know, is factory 1 the same as factory 2? Or if there's like a similar brand to M&M, M and M and M, 3 M's, are those two equals? Now we can do a bigger study and see, is factory 1 and factory 2 when looking across different types of bags of M&Ms, and we could generalize that even further out. We'll see later when we do random effects models, it even gives us a greater ability to generalize in some cases. We're going to be dealing with fully crossed models, which means we're going to be combining every level of our A and B, or whatever many levels we have for our independent variables. If we didn't have every level, we'd have a nested model, and we'll look at those later in the semester. In this case, for our fixed effects models, levels are fixed, which just means the researcher chose them, or by default, they're the only levels that exist. So, if you choose the bags of M&Ms, or you choose ethnicity you would like to look at, then you have selected those as fixed factors. If you choose categories of age, instead of randomly selecting age categories to examine, those are fixed factors. Each person will respond to one combination of our factors, or basically each person is in one cell, one condition, and the levels are selected by us, the researchers. Ideally, we would love to have a completely randomized factorial design. So let's take a look here at the model. We went through this model in class. I'll go over it in a little more detail in a second. But we went over it last time with just a main effect of A, or main effect of a one-way analysis of variance. But we have Yijk, Y sub ijk, plus equals mu, the gram mean, plus alpha, the effect of being in factor 1, for factor 1, plus beta, the effect of factor 2, plus alpha times beta is just the interaction effect plus error. Last time we had mu plus alpha plus error. All we've done is extend this model out a little bit. And our general layout of this data I have put here as level A, 1 and 2, and level B, 1, 2, 3. Also see the video. Again, I'll point you to the other video. It's a little more fun than this one probably, where I go over the 2-factor ANOVA with 2 levels, and that will have a very similar layout of data as here. So in this layout of data, I'll kind of escape out of here just for a second so you guys can see me highlight stuff. This is level A. We have 2 levels, A1 and A2. Level B has 3 levels, level 1, level 2, and level 3. And we can see in level A1 and B1, there's people, or there's things we're counting, and that creates cell 1. And now we can go across A1 into B2, and we can see there's people in there too. Y111 just represents Y, person 1 in category JK, basically in, this is person 1 and person 2, see 1 and 2, in A level 1, B level 1. We go down here, we say this is person 1, a different person, in A level 2, B still level 1. See, we're still in level 1 for B. And then we can do the same thing here. If we went to B3, A1, we can see this is person 1, A1, B level 3. And that helps you read what these subscripts are saying up here. I is person, J in this case is the level A that you're in, which of the 2 levels for that independent variable, and in this case, K is which of the 3 level B's that you're in. Hopefully that'll help. These out here are the marginals. This is if we averaged over. We went across A. We went from A1, B1 to B2 to B3, and we got the average. And then if we went down this column here, we would get the average being within B1. So across A1 and A2, and this Y bar here represents our gram mean. I'll reiterate some of this slide in class as well. And other thing I do is I just bring up Lomax and Hausfall's table in the textbook. This kind of shows you the same exact thing, just a little bit more robustly. I'm not going to go over it again, but I will follow up and touch on this in class a little bit. And in general, cells, and also in my other video for looking at interaction and main effects. All right, so let me go back to the slideshow. And how do we reduce error? Let's see. In our one-factor model, the interaction effect gives us more information. We get more information with our interaction effect than having two separate one-way ANOVAs. So here's one-way ANOVA 1. This is exactly the model we showed in our last class and some of the other videos. Mu plus alpha plus error. Gram mean plus effective B in your group plus your personal effect, the residual error. If we just did a one-way analysis of variance on the second factor, we would have mu plus beta plus error plus E plus epsilon. So all that at B now is that's the main effect for being for our independent variable B. Beta is B in this case. Now we have our full model, which is mu plus alpha plus beta plus the interaction effect. We can see that if we just test a one-way analysis of variance with our first factor, we just get the variance partitioned out, that is for alpha. And if we do it just for our second one-way analysis of variance, we get beta. But in this case, we now get three terms. We can more narrowly focus. It's kind of like being able to go to this cell level instead of across those gram means. So the interaction effect gives us more information. We can separate it out, as I said, and we also can partition and reduce the error further. So this is error. If we just used alpha, we can circle all that stuff. That's how much more we're breaking up that error term. So we can think of it as if you just had the first factor, the only factor you cared about. If we were doing M&Ms by bag type versus M&Ms by factor, and we ignored the factory effect, we would be kind of in that error here. All of the other effect of the factory and the interaction effect it might have with the bag type would be lost. It's just kind of encompassed in error. But now we're kind of breaking up error, making it smaller and smaller, and we're explaining more things. That's basically what we're doing. Assumptions. I write it this way because I think of NIH. You can think of whatever you want, but I think of the basic assumptions for analysis of variance very similar to our t-test assumptions. We assume normality, we assume independence, and we assume homogeneity of variance, equivalent variances amongst groups. We assume that, central limit theorem helps us out a little here, but we basically assume that at around sample sizes of 25 and 30, that the means that we would be sampling from would be normally distributed. And also independence. We don't want to overlap people into multiple groups, then there's going to be a dependency issue. Here is our analysis of variance sums of squares tables for a two-factor analysis of variance. I'll just quickly go over this, and we'll follow up with this in class as well. We see that A, that's the main effect, source of variance for our factor 1. B is our main effect and factor variance, source of variance for our second independent variable. And B, AB, that's the interaction effect. So we can go across A. So going across A, we see we get sums of squares, we get degrees of freedom, which are j minus 1, number of groups of A minus 1. We get the mean squares by just taking the sums of squares and dividing it by degrees of freedom. We could look across, go take the sums of squares, put it in the numerator, take the degrees of freedom and put it in the denominator, and we get our mean squares. Remember, mean squares is another way of talking about variance, and it's a variance or mean squares related to the source of variance A. Then we take that mean squares A and divide it by mean squares within. That's our error variance. We can do the same thing here, take sums of squares within divided by degrees of freedom, and we get mean squares within. We take that ratio, that's your F value for our source of variance for main effect A. But notice here the thing that's changed, instead of one F value, we're going to have three F values for our two-factor model. We need to do the same thing for B, take our sums of squares. In our example, previously we had 2 different levels of A and 3 different levels of B. So 3 levels of B, that would be K is 3 minus 1 is 2. And we would take sums of squares divided by degrees of freedom here, and then take the mean squares of B that we get and divide that by mean squares within. Then we have an interaction effect, and this is kind of neat. We take sums of squares of A and B, the interaction effect, and we divide that by J minus 1 and K minus 1. So if you get degrees of freedom here and degrees of freedom here and cross multiply them, That's your total number of degrees of freedom. So in this really simple example, if j was 2 and k was 3, j minus 1 is 1, k minus 1, if we had 3, so 2 minus 1 is 1, 3 minus 1 is 2. Cross multiplying them gives us 2. That's what our denominator would be here. Same thing, divide by the sums of squares of a, b, the interaction effect, and we get means of squares ab, divide that by mean squares within. And mean squares within in class previously, we just did n minus number of groups. Now it's n minus kind of number of cells. That's j times k. So if we had 2 times 3, that would be n, whatever our total, whatever our n is, minus jk, and total is still n minus 1. Again, this is just so you have this to refer back to. You have the textbook to refer back to, and we'll talk and support this more in class. I just give you this as a table. You also have this in your PowerPoint, in your notes from the Blackboard site. But this is broken out the sums of squares so that if we were to calculate these out, which we're not going to do in this video, but that you can see, like if you did sums of squares the longhand way, where those are coming from. And just quickly, we can see that this is the effect, this is your group mean for A overall, kind of marginal for anybody in A. This is anybody in B, and then we subtract both of those respectively by the gram mean. So that represents the effect of being in A minus, whether you're in level 1 or 2, minus the gram mean. This is whether you're in level 1, 2, or 3 for that previous example, minus the gram mean. Here, all of this really is doing is this puts you at the cell level. You take the effect of being in your cell minus A minus B plus the gram mean, and that ends up giving us a cell level effect of sums of squares. Error is still the same, and total is basically still the same. Little slightly different with those summation signs, but within those parentheses, we're effectively doing the same things we've done before. I just show you this to not to freak you out or anything, but we have a 3-factor model. All we're doing is we're extending that linear model out. We go from just having alpha and beta to having alpha, beta, gamma. We have 3 different main effects, and we can create an interaction for each. We have alpha times beta, alpha and gamma, beta, gamma, and then we have a 3-way interaction effect also. So we have 1 3-way interaction effects, 3 2-way effects, and 3 main effects. But one caution is when you start to get to 4 interaction effects or more, it can just be difficult to explain what's going on based on theory. So really think through what you're putting into your model, and don't just throw in effects just because you can. Think them through and be a smart researcher. Multiple comparison procedures are going to be very much the same as we did before. One of the big differences is that I like to plot the interaction effects, as you'll see in my other video. And most complex comparisons, we can start plotting them to see what type of effects that we have. Here's just our sums of squares total. We see that how it's partitioned should be starting to be some intuition around here that the partitioning of sums of squares is the total is broken up into sums of squares of A plus sums of squares of B plus the interaction of sums of squares AB plus the sums of squares within. So we're basically getting down to the cell level and building back up if we wanted to think of it that way. So A plus B plus interaction plus within gives us sums of squares total. And here's another look at our total fixed effects model for our table, but this time I've added in our expected mean squares. I'll just talk a little bit about these and follow up with this in class. I know sometimes expected mean squares can be a little confusing, but let's just say expected mean squares. Let's go to the within model here. We see EMSA. That's the expected mean squares. So we have mean squares, which we know are variance components. How much variation is there due to just being to the within group. And what we can do is just say that what we expect to find, this term really is when the null is true. We just expect to find this sort of variation that's the source of variation is just due to this error term. But what we see in each one of these going down the column is that it's the error term plus some effect. I'm not even going to go into details in this video, but this is just showing this is the effect due to alpha, and this is the effect due to beta, and this is the effect due to the interaction of alpha times beta. So what this is saying, when the null is false, that is, we've rejected the null, that means that there is a difference that we think is meaningful or significant, relatively large, that we say, well, the terms that are making a difference are both the effect of within group error, just the source of random error fluctuation, the error term in the denominator that we would expect, plus we have this effect of an interaction, or we have this effect of a main effect. If the null hypothesis were true, the only thing that would really be in that primary term would be the source of variance just due to random fluctuation, just due to the error term in the denominator. So if you were to take this as your numerator and the within as your denominator, we get a ratio of 1. But if the main effect of A is true, then you have 1 plus some effect of being in A. And you have 1 plus some effect of being in B, and 1 plus some effect of being in the interaction term. So the idea here is when we think about expected mean squares, that we can sort of put this in as a ratio of what is expected, which is just the denominator within, which is kind of what we do anyway, right? Mean square within is in the denominator, and mean square between, well, that's in our numerator. And we sort of, over time, if we just had random data, we didn't really have real groups, we just randomly selected people to be in groups, and we didn't test anything, we would expect there to really be no difference, and the null hypothesis would be held up, and we would expect just the difference between groups just to be due to random fluctuation. Again, we'll cover more of this in class, and after we do, you'll come back to this video again, and hopefully that'll be a refresher. Our eta and omega are slightly different. Before, we could just take eta and divide it by the total sums of squares. Now we're breaking it up. We have sums of squares A is actually sums of squares A plus within, sums of squares B divided by sums of squares B plus within, and sums of squares AB divided by sums of squares AB plus within. I think you can see the pattern going there. Eta is going to be easy. Omega, I'm not going to go through each one of these. You can kind of look at the differences here. But what you're seeing is the effect of sums of squares A, sums of squares B, and sums of squares AB, whereas the rest of the model is pretty much held constant. So that's how we would calculate omega. We'll practice one of these and do eta, partial etas and omegas in class. And then this is just to see if we extend out the model for a 3-factor model, this is what it would look like. I'm going to go ahead and end there. I won't go through this in detail, but you're welcome to ask questions in class and also play around with this in SPSS for some of our examples.